Hi everyone, this is lesson 2-4, Zeros of Polynomial Functions. Our video is 2.4.7 and 2.4.8, and our learning target is for students to be able to factor and find the zeros of a polynomial function and find the zeros of a polynomial when one is known. So the first half of this video will focus on you being able to factor and find the zeros of a polynomial function. In the second half, we'll talk about finding the zeros of a polynomial when you know one of the zeros already. Alright, so we're talking about factoring polynomial functions over the real number system. And this key concept here talks about every polynomial function of degree. Again, remember, degree means the highest exponent of the polynomial. Our degree has to be greater than 0. And our polynomial has to have real coefficients that can be written as the product, multiplying, of linear factors and irreducible quadratic factors, each with real coefficients. So the word linear, remember, is a degree 1 polynomial. A quadratic is a degree 2 polynomial. And the only time you're allowed to have a degree 2 polynomial or a quadratic factor is if it is irreducible or not factorable. So we'll look at that in further examples, but I just want to talk about how to factor polynomial functions and how you know when it's factored all the way. A polynomial is factored all the way when it's written as the product of linear factors and irreducible or non-factorable quadratic factors. Alright, so in this example, part A, we're going to consider the polynomial function k of x equals x to the 5th plus x to the 4th minus 13x cubed minus 23x squared minus 14x minus 24. And we're going to write k of x as the product of linear and irreducible quadratic factors. Now, in order to do that, we need to know what the zeros of this polynomial function are. Okay, first of all, I know that this function, since it's a degree 5 polynomial, could have 5 zeros because the highest number of zeros a function can have, or a polynomial function for that matter, is equal to its degree. So if we have a degree 5 polynomial, then we could have up to 5 zeros. If we have a degree 4 polynomial, then we could have 4 zeros, etc. So a degree 5 polynomial, it's possible that we have 5 zeros. And what I can do is I can use the rational zero theorem, or I could graph this polynomial to see what its zeros are. So I'm going to go ahead and graph k of x on Desmos and see what my zeros of this function are. Alright, so after graphing on Desmos the polynomial function k of x, I can see that its zeros are at x equals 3, negative 3, x equals negative 2, and x equals positive 4. So even though we said there's a possibility of having 5 zeros, 5 real zeros, we actually only have 3 zeros that are real or show up on the graph. Again, we have 2 right here at negative 3 and negative 2, and another one at positive 4. So what I want to do is I want to write out this function in factored form with its linear factors and its irreducible quadratic factors. Because I am missing 2 zeros, because there was a possibility of having 5 zeros, I am missing two of my zeros. And what that's telling me is that those 2 zeros are imaginary, and they come from an irreducible quadratic factor because, remember, a quadratic is degree 2. So it would make sense that if our quadratic If we had a quadratic factor, that quadratic factor would produce these missing two zeros. So on the next slide, I'm going to go ahead and continue our factorization of this polynomial. Okay, so on the last slide we decided x equals -3, x equals -2, and x equals 4 were the zeros of our polynomial function. Now, if x equals -3 is a 0, that implies that x plus 3 is a factor. Now, how do I know that? Because if I were to substitute -3 in here for x, -3 plus 3 would equal 0, and we know that -3 is the 0 of the function. So, moving forward, then if x equals -2 is a 0 of the function, that means x plus 2 has to be the factor. And if x equals 4 is a 0, then x plus 4 is a factor. Now, to determine, we said there was two zeros that were missing here that come from a quadratic factor. And to figure out what that quadratic factor is, we need to use synthetic division. So what I'm going to do is I'm going to use -3 as my divisor. And my coefficients were 1, 1, -13, -23, -14, and -24. So I'm running out of room here on the edge of the screen. But what I'm going to do is I'm going to carry out the synthetic division and prove that my remainder is 0. So if I carry down the 1, I get 1 times -3, which gives me a -3 here. I'm going to add my column, which gives me -2. When I multiply -2 by -3 here, which is my divisor, I get a positive 6. If I add -13 and 6, I get -7. When I multiply -7 times -3, I get positive 21. When I add, I get -2. And when I multiply -2 times -3, I get a positive 6. And when I add this column here, -14 and 6, I get -8. And when I multiply this -8 times -3, that gives me a positive 24. So when I combine that with -24, I get a remainder of 0. So what does that leave me with? That leaves me with my remaining polynomial with -8 as my constant. X is going to be -2x, -7x squared, -2x cubed, and 1. Oops, that should be cubed, and this should be to the 4th power. Now, what I'm going to do is I'm going to then take these coefficients and divide them by my next factor, which I already used -3 as my 0, but I'm going to use a factor of x plus 2, which means my divisor is going to be -2. So on the next slide, I'm going to take these coefficients right here at the bottom, because my remainder was 0, and I'm going to divide them by -2, which is another 0 of the polynomial. Right, so we're going to keep going here with our synthetic division. Again, x equals -2 is another 0 of my polynomial, and again I use these coefficients from the remaining that were left over or remaining after I completed the last synthetic division with the divisor of -3. So I'm going to carry down 1 right here times -2 is going to give me -2. When I add my column, I get -4. A -4 times a -2 is going to give me a positive 8. When I add my column, I get 1. And when I multiply 1 times negative 2, I get negative 2. When I add this column, I get negative 4. Negative 4 times negative 2 is positive 8, and of course, I should get a 0 for my remainder. Now, if 0 is my remainder, then negative 4 is my constant, 1 is my coefficient of x, negative 4 is my coefficient of x squared, and 1 is my coefficient of x cubed. So, we still have one more 0 that we haven't used for synthetic division, and that is x equals positive 4. So what I'm going to do is I'm going to go down here and divide by 4 this time, but this time I'm going to use these coefficients because again, if I get a remainder of 0, then I can use these coefficients as my remaining polynomial. So I have 1, negative 4, 1, and negative 4, and I'm going to carry down the 1, and 1 times 4, 1 times my divisor of 4, so 1 times 4 is going to give me positive 4. I get a 0 there when I add that column. 0 times 4 is going to give me a 0. When I add this column, I get positive 1, and 1 times positive 4 gives me 4, and I get a remainder of 0 again. So I have a remainder of 0. My constant is 1. I do not have an x term because my coefficient is 0. And then I have an x squared attached to the 1. So when I go to write this polynomial in factored form, we've already determined that x plus 3 and x plus 2 and x minus 4 are factors because negative 3 was a 0 for this factor right here. Negative 2 was a 0 for this factor right here. And 4 is a 0 for this factor right here. So what does that mean? That means that my leftover factor, my remaining factor, comes from these coefficients, which would, when I write that out, would be 1x squared plus 1. And this quadratic is irreducible, x squared plus 1. This factor right here actually produces 2 zeros. And each of these only produce 1 0 because our power on the x is 1. Now, these two zeros don't actually show up on the graph because that x squared plus 1 factor is irreducible, meaning x squared plus 1 cannot be factored. And if you think about it, x squared plus 1, if you set it equal to 0, that gives me x squared equals negative 1. And if I square root both sides, x equals plus or minus I. So the other two zeros that exist for this polynomial, at the very beginning I said there was 5 zeros. It just, when we graphed it, we only saw 3 zeros on the graph. So we had 3 real zeros at negative 3, negative 2, and 4. And the other two zeros for this polynomial are imaginary. So we won't see those on the graph of the function. So we have factored our polynomial. That was the whole point of this, is to come up with a factorization of the polynomial. So if I multiplied all 4 of these factors together, I would get the original equation, x to the 5th, and then all those other terms. So we are done with this question and ready to move on to the next part. Now this is going to go relatively fast because we've done a majority of the work already for this problem. What they want us to do, they gave us the same polynomial, but now they want us to write k of x as the product of linear factors. And we already had 3 linear factors, x plus 3, x plus 2, and x minus 4. And the remaining factor, again, was x squared plus 1. And this right here, I kind of lied in the fact that it can be factored. It's just that the way that we're going to factor it is by using the imaginary solutions. So this isn't factorable over the real number system, but it is factorable over the imaginary system. And remember on the last slide, I showed you that here, if I solve this for x, I get plus or minus I. So what this actually factors into is x plus I and x minus I. And the way that we get that is because we're going to subtract, we're going to take x minus a negative I, which would give us an x plus I, and we're going to take x minus a positive I, which gives me x minus I. So the other two factors for this polynomial, there are 5 linear factors, x plus 3, x plus 2, x minus 4, and the other two factors come from those two imaginary solutions of positive I and negative I. So this is the answer for part B. We have factored out the polynomial completely by writing it as a product of its linear factors. And again, to explain what linear means, it means that the x variable, all of the factors have to have an x to the first in order to be written as a product of linear factors. Alright, so part C, same polynomial. And guess what? We're pretty much done with this question already because it's just asking us to list what all the zeros are. So all the zeros, we already found 3 of them from the graph, negative 3, negative 2, positive 4, and the 2 missing ones that we didn't see on the graph that were found from taking x squared plus 1 equal to 0 and solving for x again gives us plus or minus I when we square root both sides. So the other 2 zeros are positive I and negative I, and we have our 5 zeros for the polynomial function, and I knew there was going to be 5 zeros, or there should be 5 zeros, because our degree of our polynomial is 5. Alright, so here we go. Check for understanding. I would like you to write the function, polynomial function k of x. This time we have a quartic function, or degree 4 polynomial. And I would like you to write it as the product of its linear factors. So I would like you to go ahead and the way you can start writing your linear factors, the way I did it, was by graphing this polynomial and picking out what the zeros are on the graph. Again, in the end, just because it's a degree 4 polynomial, I know that a degree 4 polynomial should have 4 zeros, thus it should have 4 factors. So go ahead and work this problem out, and then press A, B, C, or D to submit your answer. Okay, so looking at this polynomial function here, what I would like you to do is look at the graph, and you can see that we have zeros at -1 and +1. So this quartic function should have 4 zeros. We have a degree 4 polynomial, which means it should have 4 zeros and 4 factors. Now, 2 of the zeros are on the graph, so if we should have 4 zeros, we're missing 2. Which means that this function, when written in factored form, is going to have an irreducible quadratic, and or it has the other 2 zeros are imaginary, because we can't view them on this graph. Again, we only have -1 and +1 as real zeros. So x equals 1 and x equals -1 are the zeros of our polynomial. So if x equals 1 is a 0, that means that x minus 1 is a factor. And if x equals -1 is a 0, then x plus 1 is a factor. Now, to show what the remaining factors are, I can use synthetic division using positive 1 first. I'm going to use synthetic division, and I get, my coefficients are up here, 1, negative 4, positive 4, positive 4, and negative 5. And if I carry down the 1 times 1 is 1, negative 4 plus 1 is negative 3, negative 3 times 1 is negative 3, 4 plus negative 3 is 1, 1 times 1 is 1, 4 plus 1 is 5, 5 times 1 is positive 5, and I get a remainder of 0. Okay, so when I go to check, when I go to check negative 1 or use negative 1 as a divisor to show that negative 1 is a 0 of the polynomial, I'm going to use these coefficients. So I'm going to get negative 1, and then my coefficients are 1, negative 3, 1, and 5. Again, those are from our previous synthetic division. And if I carry down the 1 times negative 1 is negative 1. If I add negative 3 and negative 1, I get negative 4. Negative 4 times negative 1 is 4. 4 plus 1 is 5. And 5 times negative 1 is negative 5. And I get a remainder of 0 here. And these numbers here are my irreducible quadratic. So I have a c, an x, and an x squared. And so that means that I have x minus 1 times x plus 1 times x squared minus 4x plus 5. Now, I realize that this is one of your choices in the multiple choice question. However, the question is asking us to write the function as a product of its linear factors. And that means that this right here, this quadratic or degree 2 polynomial, has to be rewritten as a product of linear factors. Well, if you think about this, this right here is not factorable. And so in order to write it in factored form, we have to find its solutions. Now, I cannot graph this to find its zeros, because otherwise, if it had real zeros, those zeros would have shown up on the graph up here. So the solutions to this are imaginary, and the way I'm going to find them is by using quadratic formula. Alright, so we're going to find the solutions to this quadratic that's not factorable, because there are no two numbers that multiply to be 5 and add to be negative 4. So, to do that, we're going to say x equals negative b plus or minus square root b squared minus 4ac, all divided by 2a. And when I substitute in my coefficients, remember a is 1, b is negative 4, c is my constant, 5. And if I take the opposite of b, since b is already negative 4, I'm going to put in a positive 4 there. Plus or minus square root, negative 4 squared is 16, minus 4 times a is 1 and c is 5. And when I divide that by 2a, 2 times a, or 2 times 1 is 2. So when I simplify here, I get 4 plus or minus square root of 16 minus 20. If I multiply these three things together, 4 times 1 times 5 is 20. And I'm going to divide by 2. And I get 4 plus or minus square root of negative 4 all over 2. Or 4 plus or minus, now square root of negative 4, since the square root of 4 is 2, and this is negative underneath the square root, I will say my solution is 2i. Now, another way to look at that is square root of negative 4 is equal to the square root of positive 4 times the square root of negative 1. The square root of 4 is 2, and you should know from advanced algebra that the square root of negative 1 is equal to I. So that is where I got 2i here. And then I divide all that by 2. And since I can divide all of both of these factors on top by 2, I get 2 plus or minus I. That means my other zeros for this polynomial are 2 plus I and 2 minus I. Now, what does that mean in terms of my factorization? On the next slide, I'm going to go ahead and write out the entire polynomial, that degree 4 polynomial in factored form. So our polynomial should be x plus 1, x minus 1, because -1 and +1 were the zeros of the function that we found from our graph. And then we have x minus 2 plus I and an x minus 2 minus I. Again, the 2 plus I and the 2 minus I, we found those zeros, those imaginary or complex zeros, using the quadratic formula. So, our answer to the multiple choice question is C. Okay, so moving on to the next part of the lesson, finding the zeros of a polynomial when one of them is known. We're going to find all complex zeros of the polynomial function p of x, given that x equals 2 plus 5i is a zero of the polynomial function p. We are then going to write a linear factorization of p of x. So one thing that we know with with complex zeros is that they come in conjugate pairs. So if x equals 2 plus 5i is a 0, then we know that its conjugate, 2 minus 5i, is also a 0 of the polynomial. So what I'm going to do is find the remaining. We have 4 zeros, or 4 linear factors for this polynomial, because our degree is 4. And I know 2 of the zeros already. So I'm going to find the other 2 zeros by using synthetic division. So I'm going to start dividing by 2 plus 5i. That's my divisor. And what I'm going to do for my coefficients are, if I look at this polynomial function, my coefficients are 1, -6, 35, -50, and -58. And when I carry out synthetic division, this is going to be a little more difficult because of the nature of our divisor. So I start the process the same. I carry down my 1, and I'm going to multiply this 1 right here by my divisor 2 plus 5i. So when I multiply 1 times 2 plus 5i, I get 2 plus 5i. Now, when I add this column here, I have to combine like terms. And the I term, the I part of the term, cannot be combined with either the -6 or the 2. So, what I'm going to do is I'm going to combine the real numbers, -6 and 2, which gives me a -4. And since the 5i cannot be combined with anything else, I'm just going to carry that down. So when I combine -6 and 2 plus 5i, I get -4 plus 5i. Now what I need to do is I need to multiply this -4 plus 5i times 2 plus 5i. Okay, so right here I'm going to do a little bit of work. I'm going to multiply 2 plus 5i times -4 plus 5i. And if you look at this, it's a binomial times a binomial, so I will FOIL. So when I FOIL, 2 times -4 is -8. 2 times 5i is 10i. 5i times -4 is -20i. And 5i times 5i is 25i squared. Now, if I simplify this right here, one thing is that I squared right here is -1. So I squared is the equivalent of -1, then this really becomes -25 because I have 25 times -1. So if I combine that negative 25, because this is really negative 25 right here, if I combine that with negative 8, I get negative 33. And if I combine the imaginary terms, 10i and negative 20i, I get negative 10i. And when I add the columns here, when I add this column, when I add 35 and negative 33 minus 10i, I get 2 minus 10i. Now, if I have 2 minus 10i, 2 minus 10i times 2 plus 5i, I'm going to multiply them. I'm going to FOIL again. So I'm going to erase my work down here to give me some space. And I'm going to multiply 2 plus 5i and 2 minus 10i. And if I FOIL that out, I get 4 minus 20i plus 10i minus 50i squared. And if I combine like terms here, again, I squared is negative 1. So this really is going to be a positive 50 plus 4 is 54. And when I combine negative 20i and positive 10i, I get a negative 10i. So when I add this column here, negative 50 and 54 can be combined, which gives me a positive 4, and then I cannot combine the negative 10i with anything, so I just carry that down. So one more time, I have to multiply 4 minus 10i times 2 plus 5i, and I'm going to go ahead and erase some of my work right here. Oops. It won't let me erase it. Well, I guess I will have to, okay, here it goes, maybe. Nope. So it's not going to let me erase. So I'm going to go to the top of the screen here and multiply 4 minus 10i, right here, times 2 plus 5i. And if I multiply those out, I get 8 plus 20i minus 20i minus 50i squared, which then the 20i and the negative 20i cancel out. Negative 50 times negative 1, because I squared is negative 1, should give me positive 50. So when I combine positive 50 with the 8 from the front, I get a positive 58. And what do you know? I get a remainder of 0, which I should get because 2 plus 5i is a 0 of the polynomial. So on the next slide, what I need to do is I know that I have another 0 at 2 minus 5i, right? We have 2 minus 5i here. When I carry out my synthetic division with 2 minus 5i, I do not use these coefficients at the top, but rather I use these coefficients from the bottom. So on the next slide, we'll go ahead and carry that out. Okay, so we are going to carry out our synthetic division using 2 minus 5i. This should go a lot quicker than the previous 0. If I carry down the 1 and I multiply 1 times 2 minus 5i, I get 2 minus 5i. And when I add this column here, the 5i's are going to cancel because it's positive 5i and negative 5i. And I'm going to combine negative 4 and positive 2 to get a negative 2. Now, when I multiply negative 2 times 2 minus 5i, so I'm going to do negative 2 times 2 minus 5i right here. I use the distributive property, and I get negative 4 plus 10i. So I'm going to record that right here, negative 4 plus 10i. And again, when I add this column, the negative 10i and positive 10i will cancel, and I get a negative 2 when I combine positive 2 and negative 4. So when I multiply this negative 2 times 2 minus 5i, it's the same work that we had just right here. So my response again is going to be negative 4 plus 10i. And when I have a negative 4 plus 10i here, and I add this column, 4 minus 4 is 0, and negative 10i plus 10i is also 0. So, we have shown that 2 minus 5i is a 0 of this polynomial, and our remaining factors come from the quadratic of x squared minus 2x minus 2 equals 0. And to find the remaining zeros, I can either choose to factor this polynomial, I can use quadratic formula, I can graph it and find the zeros. So I think this is factorable. What two numbers multiply to be negative 2 that also add to be positive 2? Let's think about that for a second. Maybe it's not factorable. Negative 2 and positive 1 multiply to be negative 2, and positive 2 and negative 1. So it looks like it's not factorable because neither of these pairs add up to be negative 2. So I think on the next slide, what I'm going to do, just to speed up the process, I could use quadratic formula. So I'm going to go ahead and use that quadratic formula on the next slide. Alright, so we have a coefficient A of 1, B is negative 2, and C is negative 2 as well. Reminder that quadratic formula is negative B plus or minus B squared minus 4AC all over 2A. And that gives us a positive 2 plus or minus square root of 4 minus 4 times 1 times negative 2. So just to reiterate why this right here was is a positive 2, because this right here says opposite of B, and since B was already negative, an opposite of a negative 2 is a positive 2. Now when I plugged in negative 2 here for B, negative 2 times negative 2, or negative 2 squared, is positive 4. And negative 4 times 1 times negative 2, we'll work that out here in a minute. On bottom, 2 times A is just 2. And so what I am left with is 2 plus or minus square root of, if I multiply negative 4 times 1 times negative 2. So if I include this negative sign here as being attached to the 4, I'm going to get negative 4 times 1, which is negative 4, times a negative 2 is a positive 8. So really, I'm going to end up with a 12 under this square root, because this right here in the black box is 8, positive 8, so I'm going to get a 4 plus 8. And then divide that by 2. Now, what I can do is I can break up this solution. Square root of 12 can be broken up into square root of 4 times square root of 3, all divided by 2. And if I go up here, that gives me 2 plus or minus 2 square roots of 3 over 2. And the reason why I broke 12 up into 4 and 3 is because 4 is a perfect square, which when I square root 4, that's how I got this 2. And when I look at this, I'm going to say, I'm dividing by 2 here. So 2 plus or minus 2 square root of 3 over 2. Well, both this term here and this term here are divisible by 2, so that leaves me with 1 plus or minus square root of 3. So I divided 2 by 2 to get the 1. I divided 2 square roots of 3 by 2, so 2 square root of 3 divided by 2, the 2's end up canceling out. So I'm left with 1 plus or minus square root of 3 as my other two zeros. So my actual zeros to this polynomial are 2 plus 5i, 2 minus 5i, and you end up with 1 plus square root of 3 and 1 minus square root of 3. So these are the 4 zeros for the polynomial function that we were given in the original question. All right, so it's time for you to check your understanding. Find all complex zeros of this polynomial function h of x. Again, we have a quartic function, x to the 4th power. So power 4, degree 4. That means we're going to have 4 zeros to this polynomial. And we are given that x equals negative 3i is a zero of this function. So based on that information, I would like you to find the remaining 3 zeros of the polynomial. And then choose A, B, C, or D and press submit. Alright, so what we're going to do here is I have 4 choices. First of all, I know x equals negative 3i is a 0. All complex or imaginary zeros come in what's called conjugate pairs. So if negative 3i is a 0, so is positive 3i. Now, I already know that this polynomial has 4 zeros because it's a degree 4 polynomial. It's quartic. So I know A and B aren't my choices because A only gives me 2 zeros and B gives me 3 zeros. So my answer is either C or D. Now, to find the remaining zeros, I'm going to divide synthetically the polynomial function by negative 3i. And my coefficients of my polynomial h of x are 1, 1, negative 3, 9, negative 108. And when I carry out that synthetic division, I carry down the 1. 1 times negative 3i is negative 3i. When I add this column here, again with synthetic we're adding our columns. So these are not like terms, so my sum here is 1 minus 3i. Now when I multiply this by negative 3i, I have 1 minus 3i times a negative 3i, and I distribute to get negative 3i plus 9i squared. And again, I squared is the equivalent of negative 1, so this really turns out to be negative 3i minus 9. So I'm going to take negative 3i minus 9, and when I add this column here, I get negative 3i minus 12, because negative 9 and negative 3 add up to be negative 12. Now I'm going to add, I'm going to multiply negative 3i minus 12 times negative 3i. So I'm going to get negative 3i times negative 3i minus 12. And if I use the distributive property, I'm going to get 9i squared plus 36i. Again, I can substitute negative 1 for I squared. So that gives me negative 9 plus 36i. When I add this column right here, I end up with just 36i, as the 9's cancel. And when I multiply 36i times negative 3i, I get 36i times negative 3i. That gives me negative 108i squared, and I squared is negative 1. Negative 1 times negative 108 is positive 108. And when I add the last column, I get a 0. Now, what I need to do then is take these coefficients right here and divide them by our other 0 of 3i. And I'll do that on the next slide. Okay, so dividing the remaining coefficients by 3i, I'm going to start by carrying down the 1. 1 times my divisor of 3i. 1 times 3i here is positive 3i. That leaves me with 1 when I add that column because the 3i's cancel each other out. 1 times positive 3i is positive 3i, which leaves me with negative 12 here. And negative 12 times 3i is going to give me negative 36i. And when I add this last column, I get a remainder of 0. So that leaves me with a constant of negative 12 a x coefficient of 1 and an x squared coefficient of 1. So I need to find the zeros of this quadratic function. And I think, hopefully this time I'm right, I can go ahead and factor this. So what multiplies to be negative 12 but adds to be a positive 1, because again this coefficient is 1 in front of x. And two numbers that multiply to be negative 12 but add to be 1 are 4 and negative 3. So this actually factors into x plus 4 times x minus 3, which is equal to 0. And my other two zeros then are at negative 4, because if I set x plus 4 equal to 0, x is at negative 4. And if I set x minus 3 equal to 0, I get x equals 3. So we have 4 zeros to this polynomial, negative 4, positive 3, 3i, and negative 3i. This means that my answer to the question is D.